thank you very much, Dr. Ashwin, for joining us today and for being willing to share your work. And he will talk about extreme sensitivity and climate tipping points. It's a joint work. So please, everyone, remember that we are recording this session, and the recording will be made available in the next days. And if you have questions, you can use the chat button at the bottom of your screen. And if you have technical questions, you can refer either to me or to Eliza Cook. Okay?
Yeah.
So now I will mute myself. I will stop my video. Please remember, everyone, that it's better if you mute yourself, just because the microphone can give some echo or whatever. So please, Dr. Ashwin.
Can I check that you can see the mouse on my shared screen?
Yes, I can see it.
Okay, very good.
Yeah.
Okay, well, thanks for the opportunity to talk to the TiPES group about this is some work with Anna von der Heydt, and I guess it's partly stuff that's been motivating some of the questions that we're hoping to look at in work packages 4 and 5. So yeah, we'd be very happy to have feedback on what may or may not be useful. So I'm probably talking to a group of people who are much more expert than I am on climate sensitivity. So I will skate over that fairly quickly, but then talk about possible notions of climate sensitivity and the climate attractor, how you can relate sensitivities to different regimes. I seem to have frozen. Am I getting through? Okay. And in the particular thing, if you take away one thing from this seminar, I would like you to take away the idea of a, oh my goodness, where have I ended up here? A 2-point sensitivity, what it might be, and the relation it might have to tipping points. Okay. So equilibrium climate sensitivity is probably the most important quantity that climate modelers are trying to characterize to understand how global changes in climate occur in response to CO2 forcing. And here's Charney 1979 definition. It's the increase in global mean surface temperature due to fast-acting feedback processes reaching equilibrium. So if we change the atmospheric CO2, there will be some lag in how the climate system responds. But if we assume that that lag has occurred, then what level of warming do we get? And one of the big issues in climate science, as far as I understand, is that this quantity is still relatively poorly known. So in the 5th assessment report, the projected range of global warming for a doubling of CO2 still was very uncertain, between estimates going between 1.5 and 4.5. Talking to people at the Met Office, the next assessment report seems to be possibly even worse than that. So although we've got a lot of progress in modeling, in remote sensing, observational data, and data analysis, one of the sort of conundrums is, why is this range so large, and in particular, why does it have such a long tail? if you look at, I haven't got a distribution shown here, but if you look at the distribution, you probably know that it stretches off to very high sensitivities. And here are, the left is a figure from IPCC Assessment Report 5. So you can see the range of equilibrium climate sensitivity here between 1.5 and 4.5, and different models, constraints, and instrumental data show this sort of disturbingly wide range. Similarly, on the right, if you look at paleo data and you try and estimate equilibrium climate sensitivity, well, it seems to be maybe less broad than the current ranges, but still fairly broad. And of course, the issue here is what do we mean by fast feedbacks? So, so this is something which is in a draft of a paper that hopefully will go in the next couple of months, where it shows the various different processes going on in the climate system, ranging from volcanic activity through to atmospheric aerosols. And you can see if you choose more or less any period to say the fast processes occur if to the right of some arbitrary choice, you're actually in the middle of some processes that are still going on in the climate system. So, so this is from Rowling et al. 2012. That shows that maybe more clearly for the different Earth system processes. Well, equilibrium climate sensitivity, as far as I understand, is normally examined on a sort of 100-year time scale, but that interferes quite a bit with the timescales of how the oceans and vegetation and ice sheets and the carbon cycle are going on. So it's not clear you have really a good timescale separation. So what can you do? You can try and estimate it from models, from paleoclimate reconstructions, and there are various ways to do this. I'm not going to go into those in detail, but then you're also faced with the problem, which we are very much in TiPES, is equilibrium climate sensitivity is a very linear notion. It's a sort of a linear response of the climate system to some perturbation. But if we look at, for example, in Lenton's paper on the tipping elements, there are a variety of processes where it's suspected we may have a fairly sudden and abrupt response, at least locally, to a steady and small change of input. So how does equilibrium climate sensitivity and tipping points, how can they fit together? And if you look a few years back in the literature, there was a very influential paper by Rowe and Baker, who examined the particular problem of extremes of sensitivity in the equilibrium climate sensitivity and the sort of apparent large mass there. And they suggested it actually is a consequence of the fact that we're just doing a nonlinear transformation of normally distributed feedbacks when we're calculating equilibrium climate sensitivity. And so in that approach, it's saying, well, it's a standard result of, if you like, uncertainty on certain feedback processes. So Zaliapin and Gill responded to this, and there was quite a flurry of responses going backwards and forwards, because they pointed out actually you can get extremes of sensitivity from tipping points and non-linearities in the system. So in the sense, extreme in the climate sensitivity could well be an indication that you're getting sort of critical slowing down in the system, that you have basically near a bifurcation point. And I guess, yeah, one of the things that we've done in this study is to actually show that to some extent, both of these processes can be present in causing high sensitivities. So if you want to understand in a theoretical level what's going on in sensitivity, then you probably want to look at an energy balance model such as this, where you have so the rate of change of the mean surface temperature is a response to a variety of different fluxes in and out. So you've got forcing, so that's from external radiative forcing from the sun. You have slow and fast feedback processes, and then you have the outgoing long wave radiation. You can use this notion because basically the things that you want to look at are the changes in forcing due to CO2 and the changes in surface temperature. So you can define a specific climate sensitivity, as in Rowling et al., by looking at a ratio of a small change in temperature over a small change in forcing, where we must actually take account of the slow feedback processes. So this means we can use the specific climate sensitivity to give a linear prediction for the change in temperature as a response. So we're looking at the response as corrected for the slow feedback. Thinking of this in a dynamical systems viewpoint, microstates, we can think of the climate system as a very high dimensional system that is evolving according to some dynamical rule. We'll assume that that's smooth just for the sake of argument. And so if we look at the future states, they are determined by this flow. X of t is phi t of x0. So x0, of course, is only partially observable. We can only ever observe, or even hope to observe, a very small, very low dimensional, if you like, projection of what's really determining the future state. And two particular observables we're most interested in are the global mean temperature. So we can think of that as an observation taken from the high dimensional system and just projecting onto the spatial average at a moment in time, and the radiative forcing, which you can view as also an observation from the system. So if we assume that the dynamics here are occurring in a sort of a generic way, well, if we use the standard dogma, I guess, used in dynamical systems, that there should be some probability measure that determines the behavior on the attractor, then you can look at, you can define this measure, capital M, which is a notion of a natural measure on the attractor in this high dimensional space. So this is a measure such that if we take any observable, then averaging over typical trajectories will give us the mean we would get if we averaged over the measure. And so the basic idea that we are doing here is to consider we have a high dimensional system with looking at the two particular observables. We have the radiative forcing, particularly the radiative forcing due to change in CO2, and we have the global mean surface temperature. Well, if we got the have the natural measure and we project it onto this two-dimensional set of observables, that will actually give us a measure. And when we are talking about tipping points or climate sensitivity, the approach we're taking is that we're talking about properties of that projected measure. So there are various things one can do there. If you start off with, so M is the measure on the high dimensional space, we can define this measure mu. This is like the projection onto these two observables. And from now on, I'm going to be talking about delta R, which is not the radiative forcing, but it's the radiative forcing relative to some standard reference, so pre-industrial level. So if we now consider what this looks like, so here's delta R against T schematically, and if we had an energy balance model, then there could be a branch of stable solutions such that for each value of delta R, we have one or more stable values of the global mean surface temperature, with possibly unstable ones in between. So you can see here, this would be an example. You have a stable branch here, another stable branch here, and there's an unstable branch in the middle. And so here we have saddle node bifurcations at the two edges where the number of solutions changes. But let's think of this not in terms of the energy balance model. Let's think of this in terms of the projection of the high dimensional climate system onto this set of observations. So if we consider A is the projection of the initial climate state, and we evolve these forwards in time, then they will follow these various grey and black lines. So A could end up being at C. If it passed through a tipping point, we could end up maybe at D, and so on. So there are various different and slightly inequivalent notions of sensitivity that we're looking at here. One of them is the 2-point sensitivity. So that's given any 2 points on the climate attractor, for example, A and C. If we look at the slope of that line, that defines a sensitivity. If we look at a different points, A and D, then we have another notion. So the 2-point sensitivity is a bit unusual in that it's not a linearized response at all. It's really just a geometric property of this projected attractor. Maybe the more usual notion of a climate sensitivity would be to take your point A and you look at the closest point on your model, on your lower dimensional model. So here's B, and then we look at the response of the system to infinitesimal perturbations. So that would give us the line, for example, EB, the slope of that will give you an instantaneous notion of sensitivity for this same point A. Okay, so this is all defined in the paper, and I'm not going to go into that in detail, but I'd be very happy to have some feedback about that in due course. What I'd like to hop on to now is to talk about what happens if you have more than one climate regime. So in this we have, if we put a threshold temperature here, and we say everything above this is in the warm, everything below is in the cold regime, how can we relate the sensitivity, oh, I'm going the wrong way here, how can we relate the sensitivity to the state, and in particular changes between state? So one can look at well, basically you can condition the sensitivity on whether you remain in the same regime or whether you change regime. And so formally that just means that we can consider this measure, this density of states in the forcing temperature space and we can split that into two bits, the cold states and the warm states. And then we can look at how does the sensitivity, is that a predictor for a change in regime? So now I'll get into the model that we looked at in the first model that we looked at in more detail. If there's a bit of time at the end, there's a more complex model, which is not just an energy balance. But here's the energy balance model we looked at, which I guess is, it has features of Heydt's work and also Zeliapin and Gill. So you have the usual radiative forcing with albedo, temperature-dependent albedo. We've got a temperature-dependent emissivity as well. And then we have a forcing that is associated with the CO2 concentration. So if we consider this here as being the forcing term, that's where our delta R CO2 comes in, and various assumptions on the albedo. We're going to assume there's a shift in albedo. So the typical sort of thing, we got an emissivity, shift in emissivity and a shift in albedo. Maybe if I go forwards to these figures here, if we look at these are sort of mean temperatures along the bottom, albedo and emissivity. So there is a change of regime for the albedo. There's a slightly, well, a more smooth change, a more gradual change in emissivity. So if you put those into the energy balance model and then you plot out what are the stable states, if you look at, so this is CO2 concentration, if you convert that into radiative forcing term because of the logarithmic dependence, what you find is a curve that looks something like this. So you've got two stable regimes, and one of the things that we were trying to do with this is to ensure that those stable regimes actually reflect the fact that you could have different mean sensitivities. So if you notice, both of these are pretty straight, but in fact the slopes are slightly different. Of course, in the full system, the CO2 and the temperature are intrinsically linked through the dynamics, but to explore this in this model, what we've done is consider the case where the CO2 is actually just wandering around between some ranges of values to model the possibility that you could flip from one state to another. I should say these are not representing sort of snowball Earth or hothouse Earth. It's more like the parameters for a change between that could occur over a glacial cycle. So we put in a stochastic term to represent some subgrid processes, and you can write down where the equilibria are and so on. There's a load of parameters, and let's just have a look at a picture. So this shows a typical simulation from this model where what we're doing is we are changing the CO2 is undergoing a random walk. Well, the logarithm of the CO2 is undergoing a random walk with two reflecting boundaries, and you can see I think it's going between 50 and 1,000 parts per million. So in this particular run, you can see it goes up quite high, and then at some point it crosses a threshold, which you can see this tipping point. So what has happened here is we started on the upper branch. At some point, the CO2 has decreased to a point where we've flipped to a lower branch, and this is showing the simulation of CO2 against global mean surface temperature, or alternatively radiative forcing against global mean surface temperature. So this is the same trajectory. You can see we wander around. There's stochastic. There's a random forcing on the CO2. There's also a random additive noise on the Heydt equation as well. So you can see that if I was to look at this trajectory over very short periods of time, I could have a 2-point sensitivity, which actually fluctuates quite a lot. As I get close to here, you can imagine pairs of points that are close to this point will have a 2-point sensitivity that's very large. Actually, I should do it in this, the straight lines are in this right diagram, and then when you land on the lower branch, you can see there's a different mean sensitivity. So just let's look at this again. So this is the same trajectory where you have a sudden change in regime at this point. If we look at the instantaneous sensitivities, so that means we project onto the nearby solution of the noise-free system, you can see it's fairly constant over a long period. We've got a couple of peaks here, sort of rises here that correspond to troughs in delta R getting close to. So the lower red line is the location of the lower saddle node. The upper red line is the upper saddle node. And then as you actually hit the bifurcation, as you hit the tipping point, you can see there is a large and sort of momentary rise in the sensitivity just before. So we have looked at a couple of standard early warning system signals, in particular the detrended standard deviation and the AR1 coefficient, and you can see this, the standard deviation does grow quite substantially, but basically only when you hit the tipping point. Something we would like to do is to investigate this a little bit more and to quantify it better. With the AR1, we were really struggling to find any signal there of the approach to the tipping point. So the left one corresponds to a case where the evolution of the CO2 is relatively fast. In particular, it's not much slower than the evolution of the timescale of evolution of the temperature. If we slow down the CO2, which is what's happening on the right, then you can get much clearer signals. So this is just the same thing run with a more with a slower variation in the wandering CO2. You can see you still hit your tipping point here with the red line, the saddle node. You get the jump in temperature, but you get a very nice and if you like, measurable increase in the sensitivity, the instantaneous sensitivity in this model. Again, standard deviation we couldn't get much out of. AR1 looks a bit more promising in this case. So one of the things I guess it would be interesting to do is to quantify exactly what the timescale separations need to be to give good, reliable early warning signals, and how early can they be. So that was the case for looking at instantaneous sensitivities. If we look at 2-point sensitivities and we do this classification, and now, so this is like a depiction of the measure which was shown as mu earlier on in the talk. So this is the projection. It's like an empirical projection of the natural measure onto the forcing against temperature axis, where you can see regions of high density. So these are arbitrary units here. The purple shows regions of high density. So these regions aren't very well sampled, and they are very rarely visited. So if you can see here, there are 2 regimes. There's a warm regime and a cold regime, and they are pretty damn straight. And then we can quantify this by looking at the 2-point sensitivities. So again, that's looking at pairs of points where each point is chosen at random with respect to this natural distribution on the delta R against T. So depending on whether we require both of those points to be in the same regime or in different regimes, we'll get different distributions. So if we consider the top one here is showing the 2-point sensitivities, the distribution of them. So this is specific sensitivity, I guess, S. You can see if both states are in the warm regime, you actually get a fairly well-defined, well-constrained peak. Although what we've done here is everything on the tail is rounded to the last box. So you can see there is some mass left in the extremes here. If you consider now the probability that one state is in one regime and the other state is in the other regime, conditioned on what the sensitivity is, you can plot that out. So that is, you can view that as a sort of probability of there being a tipping point between the first point and the second point as a function of the sensitivity. You can see that almost all of that is actually in the extremes. It's not only in the extreme positives, but it's in the extreme negative sensitivities. If you consider the case where you have both states are in the cold regime, we also get something that's nicely constrained, but the mean is different. And then this is tipping the other way from the cold to the warm. So these are for runs using this energy balance model, a stochastic energy balance model with a wandering CO2. And the left and the right panels are computed in different ways. So the left panel is computed using basically taking random starting points and a range of different timescales between the beginning and the end, between the first and the second point in the 2-point sensitivity. The right panels show for the same data, but where what we do is we first just do a representation, a projection to estimate the density of this measure in the plane, and then we take pairs of points relative to that measure. And although there are definitely sampling errors, the main picture seems to be the same. Okay, so got a few. Yes, let's get on to using the same model, but for slightly different parameters. We can explore the sort of dependence of sensitivity on the presence or absence of tipping. And we looked at sort of 3 cases. One would be the default. This is as before. We could also consider a case where there is an albedo contrast, but it's only fairly small. And the third case is there's no albedo contrast. So if I go on to illustrate this projection of the natural measure onto the observables delta R and T. So this is the top left represents what I showed you just before. You have 2 climate regimes. If you look at the combined sensitivity, so now we're just taking 2 points randomly chosen and look at the slopes of the chords there, you can see a sort of a twin peaked and fairly broad distribution. The second case, we've turned down the albedo contrast so that there is now no longer any there's no longer any tipping point, but what we're left with is a strong state sensitivity, state-dependent climate sensitivity. So that's sort of illustrated on the right there. So yeah, so there's now no sudden jumps, no tipping points, but still sort of the non-linear feedbacks cause the sensitivities to spread quite widely. And only in the third case, where there's no albedo contrast and the so the distribution is very well constrained to more or less straight line, then you get a strongly peaked sensitivity, something you'd expect sort of from a normal distribution maybe. So this was some runs for a very simple one-dimensional model with wandering CO2. We also looked at a more complex, the Gildor and Zipperman 2001 model, actually with external forcing. It's got biogeochemistry in the ocean. I'm sure a lot of you know it better than I do. So you've got four latitude boxes, zonally averaged. You've got 2 layers in the ocean, 1 in the atmosphere. And this is a sort of a minimal model that actually allows modeling of Pleistocene ice age oscillations in response to Milankovitch forcing. And this is really just to illustrate, I guess, that you can play the same game here. You can compute very long trajectories for this Gildor-Zipperman model. You can extract the observations of the radiative forcing and global mean surface temperature and try and explore the relationships between them. So if you just look at the radiative forcing, you can see that actually the sort of responses you're going to get out of there are not going to be very linear at all in either of the regimes. If you look at what's happening to the land ice influence on the forcing, this is not a very well constrained sort of representation of one-to-one representation between global mean temperature and forcing. If you look at the combination of the two, however, you get a very clear sort of division into 2 regimes that have different mean sensitivities. And I guess one of the reasons for looking at the energy balance model was to try and find trying to understand that at the level of sort of energy balance. We can do something similar there with the sensitivities, the distribution of 2-point sensitivities, and the probabilities of tipping in the sense of conditional on what the sensitivity is, the probability that there is a tipping point between those 2 points. So again, the warm state is very well constrained, very tight. The cold state is much less. But again, if you look at the sensitivities associated with tipping, you can see that those are predominantly the extremes. So, in conclusion, I hope I've convinced that the 2-point climate sensitivity is a useful thing to look at, and I think it could be useful to look at in more general models. In the case where you have a sort of functional relationship between surface temperature and forcing, then you can interpret it as a slope of that relationship. But it's more general than that. It's a geometric notion. It doesn't require there to be, if you like, linearizable response. It's a purely geometric property of the the natural measure on the system. So state dependence and presence of tipping points produces some signatures in the distributions of the climate sensitivity. Of course, the interesting thing would be to go the other way in, are there things from the climate sensitivity or generalizations thereof that can be used to infer things about the presence or otherwise of tipping points. And I think, yeah, this one is this result is quite interesting in that it suggests that we need to look more closely than at the 2-point sensitivity. Certainly it would be nice to come up with some combined quantification of sensitivity and probability of tipping to give a good picture of potential changes to climate regime, and to maybe better understand the relationship between extremes of the climate sensitivity and there being a high probability of regime change. 2 models I can highlight we looked at. One is the energy balance model, and the other one was the Gilder and Zipperman model. And maybe I should pass over to Anna, if she would like to say a few things, in particular what I've left out or got wrong.
Well, I think you've said most of it. So I think we should better wait for questions and then see what happens.
Okay, I can just say, yeah, a couple of things that we are looking at further in this direction, future perspectives. One is to understand better the interaction between the timescale dynamics, the climate response, and the predictability of tipping points. Certainly, a point which I made early on is when you're trying to make predictions over timescales that actually intersect with timescales within your system, is particularly difficult. Characterizing regions of effective non-linearity of albedo and emissivity. I'd be very interested to hear from those of you running models or with observations that can give some sort of parameterization of albedo and emissivity as curves. Yes, interpretation of the time-dependent setting. I guess this gets on to what Julian is working at the moment. So hello, Julian. That's trying to understand generalizations of this measure in the presence of temporal variation of the forcing. So at the moment it's set up in the context that sort of you have a natural measure of an autonomous system. That's certainly not the case, but to what extent can we generalize this to sort of non-autonomous random measures? Okay, yeah, I think I'm happy to take questions.
Okay, thank you very much. Please, everyone, feel free to ask questions. You can either use the chat or you can just unmute yourself and ask your question. Thank you.
Hello, Elisa, can you hear me? Hello?
Hello, yeah?
Hi, this is Nicola Botta.
Hello, Nicola.
Hello, Peter. We missed the first 2 slides of your talk. I mean Marina and myself, we are together, we are here in Belgium for a seminar. And
so there's the first slide. There's a second slide.
Oh, right.
Okay.
Perfect.
Didn't miss much.
Perfect. No, that's very good. So my question is the following. So there is this notion of climate sensitivity that you start with and you have presented in different versions is a bit problematic conceptually, no, in the sense that it is a difference or a rate of change or some change or somehow the reaction of an average. For instance, in the classical definition, you take the mean global temperature, you double the CO2 content of the atmosphere, you compute another mean temperature, and you look at the difference. So isn't this a kind of fundamental problem? How I understand that there is a kind of dogma, but why are we computing the difference of averages and not the average of differences?
So I guess there are different notions of average here. When I say average, I mean spatial average.
Yes, yes, but I mean, if we had, for instance, if as a consequence of a doubling of the CO2 atmosphere, we would see that certain regions become very hot and other regions become very cold. It could be that the average is the same in spite of the fact that, you know, the average of the difference will not be the same.
Oh, absolutely, absolutely. So it's a very blunt instrument that does not say anything about what's changing locally. Just about anything could be changing locally. It's only, on the other hand, it is an extremely important policy lever. I would say it is poorly understood, or at least I understand it poorly, actually theoretically what it really is.
Understand that, but my question is, if when you are talking about in the context of TiPES, we are, for instance, talking about early warning signals. So could it be, for instance, that if we would look not at the difference of averages, but
yes, so I think presumably there will be a lot of utility in having a whole range of sort of sensitivities that characterize things like sensitivity of equator to pole temperature and whatever. So similar,
Yeah, I think this comes basically from the more historical evolution that for the equilibrium climate sensitivity, we always look at the global mean temperature, but
I understand.
for many things, this is not at all useful. And I mean,
but now this one thing is looking at that. The other thing is that now we apply that also in order to make some deduction and some inferences. And it is conceivable, at least, that when it comes to early warning signals or, you know, other attempts at predicting what is going on, that definition of sensitivity is perhaps not very suitable. I do not know. It's just, you know, I'm coming from methods for solving partial differential equations, and no one would use something like that when considering the difference between.
Yeah, I think
notion of sensitivity. It's a notion. I accept that it has some historical background, but it's a notion of sensitivity that if someone would tell me we are using this notion of sensitivity, I have to say why. It seems to be a completely crazy notion. Why don't you take the total variation?
Yeah, I think it one thing that we need to note here is that it can only be useful for as early so if you talk about early warning signals for any tipping points, it can only be useful for tipping points that actually do affect the global mean surface temperature, and that's not very clear whether these exist at all. Because as you say, most of the tipping points, they affect some regions or some extremes or so, and in that sense, I mean, this kind of sensitivity is completely useless.
Exactly, but that's the whole point. We are talking about tipping subsystems of the Earth system, and we are looking at the global temperature. I mean, if the temperature above Greenland is going to increase by 6 degrees and the global mean temperature is constant, this is not going to tell us anything about the melting of ice above Greenland.
Right, and for that one, it shouldn't be used. But I mean, I think
but there is this heritage that you are telling. So this is a very strong concept. I'm just asking myself whether perhaps for certain activities, it wouldn't be better to complement this notion of climate sensitivity perhaps with another one.
Well,
definitely.
I understand that it's very important that it is, let's say, in climate science, a very important notion, no? I'm just questioning whether it is useful.
Yeah, no, I mean, I think I fully agree with you. And I think what should be done is where this example that we discuss here still can be used for is if you have another system that has a tipping point, you can still use the same types of things, sensitivity, but then you don't need, you have to choose another variable. You have to choose maybe the regional temperature or whatever.
Yes, but you see,
right?
this generates a lot of noise, because then it means
Yes.
the studies become difficult to compare to each other.
Yes,
And
that's
it
right.
produces a kind of fragmentation in the scientific knowledge that then becomes very difficult to tackle with. But I understand the problem. I mean, it was not a criticism, it was just a question. If, I mean, we couldn't within the project perhaps also somehow discuss the adequacy of this notion of, let's say, the global mean temperature as being representative of climate sensitivity, if that would be like a topic of discussion or not.
Well, I think, yes, actually, that is in work package 4 to look at extended notions, more useful notions than climate sensitive, less limited notions than this sort of global surface temperature climate sensitivity. Yeah.
And some of the results that you were presented perhaps could also, you could also be used as a motivation for that. No, for instance, this diagram this very nice diagram where you were saying that in certain cases it's very difficult to gather signals from. I do not know. I mean, it's just something crazy that goes on through my mind since I, for the first time, heard about this climate sensitivity, and it seemed from the very beginning very strange to me as a notion.
It is. I agree.
Okay. So anyway, it's very nice that at least I do not feel alone. Also, by the way, we are 4 here.
Oh, so hello.
Even if you do not see many entries, be reassured that you had 4 listeners.
Okay.
4 listeners from Belgium, and of course many more. Okay, thanks a lot.
Any other questions?
No more questions?
It doesn't seem to be the case here from our side. We have some silence from the back row, and in the front row, we have exhausted our questions, I think. Marina?
Okay.
Well, maybe just to continue a little bit on what Nicola was commenting. So are you guys working on defining like regional climate sensitivities associated to these regional tipping points or something like that?
Well, not yet, but yeah, that would be, if you have a very specific regional tipping point element, then it would be natural to look at the relevant variables and maybe do the same kind of thing, like.
Yeah. So maybe because some of the tipping points are localized, one of the things that can be done in order to be able to compare different studies is to define pretty well some regions in which to average, no?
Yes.
Yeah.
Yes.
Well, the other thing that comes to my mind, I mean, maybe what I was saying is completely meaningless. It is possible that some of these models do actually predict, or that we have like conceptual models or like these simplified models with 4 boxes that actually do predict the change of the global mean temperature and do not obtain that change as a consequence of an averaging process. It is also possible. Then that, of course, it would be clear that, I mean, you use what you have, no? And if this is what you have, you use it. So that would be also something that perhaps could be helpful to differentiate or to explain also why certain notions are used instead of others. That's not very clear to me. I'm really no expert on those models.
Maybe actually I could make a comment on that in relation to the last example, the Gildor-Zipperman model. So that is one where you do have it does shift between, there is sort of multi-stability between different regimes, and that's due to very large but localized changes in land ice, if I've got that right.
Yeah, in sea ice also, combination with sea ice.
Oh, sea ice,
Yeah.
yeah.
Yeah, but that still is a bistability that has an effect on the model's global mean temperature, and that is something that, yeah, it might exist. I mean, if you look at glacial cycles, then this is probably a good thing to describe. And I think this is maybe also the confusion that arises here, that we have started looking at this kind of sensitivities because the plan was to have, if you have very long time series from, say, paleoclimate, you would like to get a feeling for the climate sensitivity from that.
Yeah.
While in all of the big climate models, the GCMs and the IPCC reports, usually what you do is you do an instantaneous perturbation of 2 times or 4 times CO2, and then you run the model to almost to equilibrium, but never really to equilibrium, and you sort of extrapolate. So then you don't have this time series, and you don't have access to this, what we call the climate attractor.
Yes, and then
that is again a very different thing.
Yes, and by taking averages, they are throwing away information that in the other case is not available from the very beginning.
Yes.
So that in the other case, it's very clear that you use the global mean temperature because that's the only thing that you have.
Yes. Exactly.
But in the case of GCMs,
you have much more.
There is information in this distribution of temperature that gets lost in the process of averaging.
Yeah.
And that perhaps it would be worth to, not to throw away, to keep some of it.
Yeah, you're right.
Okay, now I understand. Now I understand a little bit better the backgrounds of these things. Yes. No, thanks a lot. I'm really completely ignorant about that stuff. Sorry if I'm making kind of trivial questions, putting trivial questions.
No.
Any other questions?
Well, there is the big question of the virus, right? But I don't think it's the right place to discuss it now.
I don't think it's going to have much of an effect on climate sensitivity. One of the things that won't, yeah.
Yes.
Okay. Thank you very much.
Okay, thank you.
Yeah, thank you.
Thank you all.
Bye.
Okay. If there are no more questions, I think we can finish for today. Thank you very much to everyone who joined us. Thank you very much, Dr. Ashwin. And please remember that we still have an open slot for May, for the seminar of May. And we will send information about the recording of this webinar and the next webinar in the next days. Okay? Thank you very much, everyone, and see you next time. Thank you.